Welcome to the American Ceramic Society's course on firing of ceramics. This is Dennis Brosnan again, and I'm looking forward to our class number 3, the use of phase diagrams when heating ceramics made out of particles. Now, perhaps you have some experience with phase diagrams. If you do, you know they're just maps. They're maps of composition and temperature. And it tells you what crystalline phases and what amount of liquid is present at any given temperature. If you're not familiar with these diagrams, the first time you look at them, it might look like they're pretty complicated, but that's really not the case. So let me say that when I took this course, the professors always started with everything that was melted, completely melted. Everything was melted phase. And then they cooled off until crystalline substances precipitated out of the liquid. And they followed the cooling situation as different crystalline phases appeared. Liquid began to disappear until we got down to room temperature. The situation is I never made a ceramic that way. I always started at room temperature, working with a system of particles and heated up until sintering began. So the situation is very different. When you start with a liquid, everything is pretty much at equilibrium. And if you cool slowly, then certainly you are close to equilibrium during the process of cooling. But when you start heating ceramic powders, you're not at equilibrium. Equilibrium means you have pretty much the final reactions have taken place that are going to take place. Everything is probably pretty homogeneous, but that's not the case on heating up. So we have to deal with non-equilibrium conditions, and it's not that difficult to do. So I'm going to give you a little methodology today on how to use phase diagrams in thinking about firing ceramics. Well, last time we talked about chemical composition using X-ray fluorescence, or XRF. That provided us information on the major constituents in our material and also reveal minor constituents. And some of these constituents cause melting, and that's why I call them fluxes. In some cases, people might make deliberate additions to a mixture using something they call a sintering aid, which could be a flux or it could be present for another purpose to increase reaction rates. Nevertheless, what your viewpoint is depending on the system you have. In some cases, you might think these fluxes are contaminants. There might be minerals there that you don't want, that particularly give you some problems in firing. That's particularly true when you use crude clays dug from the ground. Less true when you use minerals that have been refined. Nevertheless, we're going to use XRF data, realizing that there are other methods to measure chemical analysis. But the chemical constituents are the ones that we track using phase diagrams, and we predict what's going to happen as we heat. Now, the mineralogical analysis, what minerals or compounds we have present, is done by X-ray diffraction, XRD. That is useful in tracking changes during firing, but it also tells us what's present in the fired product, and that gives us an idea of how close to equilibrium we might have come in firing. Last time we also talked about physical analysis, the changes that occur in the ceramic body during firing, and those included shrinkage. Of course, shrinkage usually always is a consequence of densification processes. So ceramic powders in compact shrink typically, although not always. Sometimes there can be chemical reactions that counterbalance shrinkage, but the usual tendency is for the body to shrink. And when that happens, you have the same mass or near the same mass, but lower volume. And that means that you have higher density. In addition, with shrinkage, porosity decreases typically in firing. Pore sizes change in typical diameter or average diameter during firing. Smaller pores tend to get bigger, and sometimes bigger pores tend to decrease in their size due to shrinkage of the body. In addition, these physical changes also result in strength increase and changes in other properties. So there's a lot going on. And we covered that last time because we're going to need to know that as we go forward. So today's class is going to deal with these phase diagrams or maps of composition and temperature. And my purpose today is not to make you an expert in phase diagrams. This comes with time and study, and perhaps to become an expert, you'd need a complete course in phase equilibria. I took one of those when I was, I believe, a junior level student at the university, third year student. And as I've said, once I got out into industry, I learned that I had to use phase diagrams differently since I was firing ceramics, not melting ceramics. So a lot of what you hear today is based on my practical experience in firing. Well, we have to start with a few definitions. Let's start with what a phase is. And the usual explanation is it's a volume, segment, or element in a ceramic composition of constant composition, meaning that composition is given in that volume element. You may have minerals. You may have glass, you may have mixtures of minerals and glass, and pores can be present. Here's a simple example of a mixture of components that becomes one phase, and that would be an aggregate particle of calcined bauxite, a large particle of calcined bauxite, which certainly has alumina crystals called corundum in the mixture. It has mullite in the phase between the alumina crystals, and it has some glass present. Of course, it's solidified in the substance, bauxite, and it's an aluminosilicate glass with some other elements present. So if you take a bauxite particle, a large particle, it has three phases in it, but since it's constant composition, we can consider it as one phase within the composition. Usually we're talking about a mineral of a certain nature, like mullite, as something of a phase. Glass can be another phase. Now, a phase diagram is just a map, as I mentioned, of phases at equilibrium at or after attaining a given temperature. Now, a phase diagram is pretty much a theoretical situation because most ceramic compositions don't always achieve equilibrium. They approach it. They certainly approach equilibrium because that's how the composition attains its minimum energy level. So the phase diagram is going to tell us what should be there at equilibrium, and it's also going to tell us a direction the composition is going to go as it approaches equilibrium, and that's really important in firing. Equilibrium is a state at which no further changes would take place in the mineral nature or phase assemblage in a composition. It's what we might call thermochemical equilibrium. At a given temperature, nothing else is going to happen. So that's what a phase diagram tells us. It tells us what is there because we're calling it a phase equilibrium diagram. Now, a diagram has components. A component is the simplest form of a compound as we want to describe it. In oxide analyses, aluminum oxide, Al2O3, can be a component. Silicon dioxide can be a component, SiO2. You can have multiple components. We're going to start out with 2 component diagrams and go to 3 component diagrams and talk a little bit about multiple component diagrams. Now, compatible phases are those that are at equilibrium with each other. They won't react. So if you have 2 compatible phases present in a fired ceramic, there's no further reaction that's going to take place between those at a given temperature. In the German language, sometimes they call these phases that can stand beside each other. They can coexist with each other. Now, phase boundary is a portion of a map where phases are present. So it's going to enclose a portion of the map, composition and temperature, where the phase assemblages at equilibrium are defined by something that we're going to call a compatibility triangle. Everything is compatible within that particular area. So let's look at a phase diagram. Here's a 2-component phase diagram. I'm going to take a few minutes to describe this. The composition is along the horizontal axis. It goes from 100% silica, 0% alumina, up to 100% alumina and 0% silica. So a point right here, for example, is 20% alumina and 80% silica. So all the compositions of 20% alumina and 80% silicon heating go up in this direction because the vertical axis is the temperature scale. Heating, we're always going upward. Now, in this phase equilibrium diagram, there are some things that you need to know. Each phase field is denoted by a name. And if it's a small phase field, like this one right here, denoted by these lines, enclosed by these lines, then it's going to be denoted by a name outside of the phase field with an arrow pointing to it. This phase field right in here, please ignore the dotted red line for now, is a field where mullite and liquid, meaning melted phase, is present. Mullite and aluminosilicate liquid is present. So you can see that there are several phase fields identified, mullite and corundum over here. And then there's a compound right in the middle at about 72% alumina or thereabouts. We start forming mullite. So this little triangle represents mullite. It's wide because there can be some solid solutions between alumina and mullite. But nevertheless, mullite is a compound. Mullite melts at 1880 degrees Celsius, according to this diagram. So it's a pretty refractory compound, whereas aluminum oxide melts over 2000 degrees, right up here. Silica, by contrast, has a lower melting point, down around 1740 or 50 degrees Celsius. I don't have that memorized because I can look at the phase diagram and find out what I need to know. So we have a diagram of different components with melting points, with a compound and mixtures that are not pure compounds are denoted in between. Mixtures of compounds. Now, another thing to notice is that we have up here a surface. and it's what bounds the liquid area. So you can follow this along. So everything is melted or liquid phase up here for any composition. So you can find a boundary where everything is liquid, and that is called the liquidus temperature. Above the liquidus, everything is melted. As you come down through the liquidus, we start seeing solids being formed. Okay. There's another name, and that's called the solidus. The solidus is the temperature below which everything is solid. So here's the solidus going across. The solidus is the temperature above which liquid appears. So the solidus is a phase boundary telling us the temperature at which liquid forms. That's the way we think of it in firing. Now you get over here to about 70 or 75% alumina or thereabouts, and all of a sudden the solidus jumps up to here, to 1880, because mullite has a very high melting point. And then the solidus continues over here until you get to pure alumina, where the melting point jumps up to 2040. So we have a liquidus telling us where everything's liquid. We have a solidus above which liquid takes place. And then we have phase names here. Now there's some special points on here. This one is called the eutectic right here. It's recognized by its V shape, okay? That point is called the eutectic, and eutectic means lowest melting. So the lowest melting point in the system is right here at a few percent silica. Maybe it's about 8% silica. I can't tell exactly right here. But as we go forward in composition, more alumina, then the liquidus increases up until we get to the point at which we get to the melting point of mullite. Now, this particular diagram has another point called a paratectic point. Paratectic, eutectic and paratectic. And paratectic point means that when you're heating up mullite, it will melt into another solid plus a liquid. So the solid over here is going to be alumina. And when mullite melts, it forms an aluminosilicate liquid over here. Definition of a paratectic: it does not melt into a liquid of the same composition. On heating, you go over the paratectic point and you form another solid and a liquid. Now, that's in contrast to the eutectic, where you melt a eutectic mixture and everything becomes liquid all of a sudden. So these points are interesting for us because it tells us where liquid begins to form. That's really interesting to us in firing because liquid is the substance that bonds vitrified ceramics together. Of course, it's solidified at room temperature, but we've got to form liquid and distribute it and use it as a cement, if you will, to bond the particles together in vitrified ceramics. In reaction bonded ceramics, we're going to heat something up and we're going to form a liquid and a mineral. And that mineral becomes important in bonding the ceramic together. And that's true of a lot of refractory products, porcelain products, and things of this particular nature. So I've drawn in a composition path for us to talk about. It's 60% alumina. So at 60% alumina, we're going to start heating up and we're going to form a liquid over here at the eutectic temperature, which is in this case approaching 1700 degrees Celsius. That's good. And as we further heat something up, we form more liquid. You can judge the amount of liquid and the amount of solid by something called the lever principle, which is really beyond what we need in this course, because typically in firing a ceramic, we can only tolerate a certain percent of liquid. If we get a large percent of liquid, the shape that we've made is going to collapse. It's going to deform, and we'll make a product that's obviously not saleable. So typically in firing ceramics, we like to get just a little bit above eutectic temperature of whatever system we have in order to make that ceramic center. Now, the diagram also tells us what should be present at equilibrium. I know I've skipped over these terms, tridymite and cristobalite. Those are crystalline forms of silica. We're going to talk about that in just a minute. But nevertheless, if we have this 60% alumina composition and we fire it up here to about 1600, the phase diagram says the equilibrium phases will be cristobalite, form of crystalline silica, and mullite. And that's true because I've done a lot of lab work which has quantified these substances, and I know that they're present. By contrast, if we heated something up containing 90% alumina and got into this phase field, we know that we'd have mullite and corundum, and that's true too. Now, of course, we're only looking at a two-component system, and if something else is present, then we obviously could have other phases. But that's pretty much the situation. Phase diagram's a map. It gives us some limits, some lines that tell us where everything's liquid, that tell us below which everything is solid. It tells us if compounds are formed. And it's very useful to us in predicting what is going to happen in firing. So remember that this phase diagram was temperature on the vertical axis in this map and composition on the horizontal axis and weight percent. And I like this representation in weight percent because everything I ever batched together to make a ceramic from, I batched by weight. I mixed up certain weights of each material to form a batch to make a ceramic. So weight percent is very useful. In this diagram, we still have the silica alumina system. Remember, here's silica, increasing amounts of alumina. But look down here, the horizontal axis is in mole percent. So it's a little different than the previous diagram. The horizontal axis in the previous diagram was weight percent. Well, I've never batched anything by mole percent, so if I'm using this diagram, I'm going to have to figure out what my composition is, and then I'm going to have to convert it to weight percent in order to use it. That's why I like to use diagrams that express the composition in weight percent. There's some other differences in this diagram. You can see here that we don't have the terms cristobalite and mullite. You just have the term silica, SO2. Well, that just simplifies it a little bit. Also, this diagram is a little different up here at where mullite hits the liquidus. We see another eutectic. Recognized by this characteristic V shape. We have the eutectic here that we knew about before, but this diagram shows another eutectic and a discrete melting point for mullite in mullite solid solution. So this diagram's a bit newer. It's more up to date. It represents an understanding that we now have with this particular material. And the temperature is a little bit different for the solidus temperature. And those are influenced a great deal by purity. So this would likely be a more modern diagram in a higher purity system. Well, I promised that we would talk about crystalline silica, and here it is. Now, I'm going to talk for just a minute about the difference between free and combined silica. Free silica means that we have a distinct phase of a silica crystal. Okay, we can see it. It's present in the composition. That becomes very important in a lot of compositions that contain free silica. So if we have a distinct granule of silica of some form, it's going to influence our firing strategies. Now, there's another type of silica called combined silica. Combined silica is the silica in a compound like mullite that we've mentioned. 3 moles of alumina, 2 moles of silica. It's a distinct crystalline compound. They're not separate phases. Mullite is one phase, and so it's combined. Silica in a glass is combined. It's in the glass structure. So that's different than crystalline silica. So right now we're talking about crystalline silica. So let's take a look at crystalline silica. And here are some phases. Quartz is the form that we most encounter in our everyday lives. Alpha quartz, the symbol right here means alpha quartz. The Greek lowercase letter alpha is the low temperature form of quartz that we normally see on the surface of the earth. We see very little tridymite or cristobalite, other forms of crystalline silica on the surface of the earth. So if you are using a product containing sand or using a raw material that contains a silica phase, it's likely quartz. Okay, and on heating quartz, it changes its crystal structure very slightly at 573 degrees Celsius. That's called an inversion. And it actually expands a bit. And so the density goes from 2.65 to 2.60 at 573 degrees C. And that's a volume change of about 2%. Now, a volume change of 2% doesn't sound like much, but if the mineral, the free silica, remains as quartz on heating, after heating, then on cooling, you're going to go backward through that inversion, and we're going to have a shrinkage of 2%. And that shrinkage of 2% can be pretty important. It can cause cracking if you go through that inversion too fast. So a lot of products, common clay products, aren't fired enough to have any significant concentration of other forms of free silica. But occasionally you'll find them there. So alpha to beta quartz inversion is something that we expect at 573. If you continue heating up beyond about 870 degrees, then you theoretically can convert quartz into tridymite. Now, tridymite is a new mineral. It has a different crystal structure. Therefore, we have to deal with the conversion on heating. And we go from beta quartz at 2.60 to beta tridymite, the high temperature form, at 2.27. That's a whopping volume increase of 13%. Now, of course, I've said about 870 because that's the theoretical number, and I put a question mark here because a lot of times the conversion from tridymite up to the next form, cristobalite, is very quick. So sometimes we don't see tridymite in the final fired product. Sometimes we do, but usually we'll see cristobalite. And cristobalite, of course, has a density of 2.21. So the total volume change in going from quartz, alpha quartz, up to cristobalite is a whopping expansion close to 20%. So, of course, one thing to say is that on cooling, you don't go back to tridymite and quartz. On cooling, because you've converted it to a new mineral, you'll cool beta cristobalite down to alpha cristobalite. So that's going from a density of 2.21 to 2.42. It increases in density. That means it's going to shrink. So the shrinkage of that free silica is something that you have to deal with because you have enough temperature in firing a whiteware product, porcelain product. If free silica is present, if it's not all entering the liquid phase, which it doesn't usually, you're going to go through this inversion then of beta cristobalite down to alpha cristobalite and have to deal with the consequences of that shrinkage, which usually means that you can have stress in the ceramic object once it's fired. So inversions are present alpha to beta quartz, inversions are present beta tridymite to alpha tridymite. And if you had, beta cristobalite to alpha cristobalite, and you can go from beta tridymite to alpha tridymite as well. So these are complex things that happen. And what you just need to know is if you convert something, then it's going to remain in that form, although it may have its own inversions on cooling. If you only invert something on heating and then you cool, then you're going to go back in the reverse direction. Now, the temperature of cristobalite formation, I said, is less than or equal to 1470. Theoretically, it's 1470. But I see converted, I see cristobalite formed in ceramics as low as about 1250 degrees Celsius, maybe a little bit lower than that. And so the deal is that certain impurities tend to function as mineralizers, meaning accelerate that conversion over to cristobalite. Some of the alkalis tend to do that. And so that's the reason in ceramics made from crude clays that we tend to get cristobalite above 1200 degrees, not up here, way up here at 1470. So these free silica phases influence us. In the melting relationships we've been talking about combined silica as liquids or compounds. But now we have a granule of something called free silica. And some diagrams show that and some don't. For example, here's the diagram again with mole percent. And here we have tridymite and mullite listed in this phase field. And we have cristobalite and mullite listed in this phase field. You might notice that the temperature here, where the tridymite would convert into cristobalite, is a little bit different than we saw on the last slide. Again, that's a purity deal, and it depends on when the diagram was made. Well, that's a lot to think about. Okay, and so now we're going to use the two-component diagram a little bit. And I'm going to talk about a diagram in Bergeron and Rysbud. Now, last time I gave you a link to this book on phase diagrams. It's really well written. I also gave you a link on a website accessible through the Ceramic Society that talks about phase diagrams. But this diagram in Bergeron and Rysbud tracks what happens at different compositions: 2% alumina, 55% alumina, and 75% alumina. And so here's one composition, 2% alumina, and it tells us the percent of each phase that's present or should be present at equilibrium on heating. Now they've thought about this in cooling, a melt of 2% alumina, 98% silica, and you go through the liquidus temperature up here, just below 1700, and we start forming some crystalline silica. Okay, it precipitates out of the liquid on cooling. As we continue cooling, we have more and more silica because this is percentage right here would be a certain percent of crystalline silica and a certain percent of liquid. Okay, liquid is up here. As we go below the eutectic temperature, then we start seeing mullite formed. So what will be present is silica, mullite, but we also have eutectic liquid present. Now you can look at this on the standpoint of heating. As we heat up silica and mullite, then we're going to get our first liquid formed up here at the solidus temperature. And we see that temperature right here. Same is true of 55% alumina. You can see a map of composition versus that's phase composition, percentage of each phase present versus temperature. And so the phases present are silica and mullite at temperatures on heating. There's a little bit of mullite shown here on the right side of the diagram. And you can see where the liquidus temperature is. Okay. Excuse me, where the solidus temperature is on heating. So the mullite being more refractory, it's going to persist on heating. And the silica that's present, this little section over here, as I read, is going to be present as well. Here's the composition of 75% alumina. And on melting, as we go down, you'll see that we hit the liquidus temperature. Okay, as we continue cooling, because this is the temperature axis versus phase composition, we'll continue crystallizing out alumina. The higher temperature phase always crystallizes out first. Higher temperature melting phase always crystallizes out first. And then we get down to the liquidus and we form mullite. So that should be kind of an exercise in looking at different areas on the phase diagram on heating or cooling. This diagram was presented to make you understand cooling, and we are mainly concerned with heating right now. So I just thought I'd mention some alumina silica products I'm very familiar with. A fire clay refractory. A fire clay refractory brick, the old-fashioned brownish yellow type of brick you see in many furnace linings, has a composition of about 40 to about 44% alumina. So the composition is right here. The firing temperature is up in this area right here. So at the condition in which you buy the refractory, the constituents ought to be cristobalite and mullite. Okay, we shouldn't get much liquid formed until we get up to the eutectic temperature, and the eutectic temperature is down here upwards of 1650 degrees Celsius. Typical firing temperature is about 1350. So we actually fire the temperature down in this particular area, fire the refractory down in this particular area. Get up to 70% alumina refractories, then the refractoriness or ability, the melting points increase very significantly. And refractoriness just means the ability not to slump or lose their shape, creep at practical temperatures, and 70% alumina products are typically fired up around 1500. So you can see that as we increase the alumina content, the firing temperatures are going to increase, and we get up here to 90% alumina, which is about in this area. The refractoriness is pretty high, and the phases in the product should be mullite and corundum, and that certainly is true, but not everything there. Now, if we want a little bit of liquid present to help centering any of these products, which we do, this diagram says we have to get up to pretty high temperatures, up to the eutectic temperature here, in order to get some liquid. So obviously, if we fire these temperatures at lower temperatures, something else is going on. Something else is contributing to liquid formation. And so the two-component diagram is, this one is just insufficient to consider what is happening. So I have another couple of two-component diagrams here for you to think about. And since it's an alumina silica composition, I've looked at some alkali silica phase diagrams. This is the soda silica, sodium oxide, silicon dioxide phase diagram. And we're interested in something up here very close to the silica axis. What happens when you add a little bit of sodium oxide to silica? So the melting point of silica itself as a mineral goes from way up here, close to 1700, down here to this point, which is around 800 or so degrees Celsius. We form the first liquid down here. So sodium oxide is a very powerful flux on silica. Now here's the potassium oxide silica phase diagram. You see potassium oxide here. It's only a part of the phase diagram, the two-component system. We're not interested in 100% potassium oxide. We're only interested in what happens if you add a little bit of potassium oxide to silica. And look at the new melting point down here around 600. Potassium oxide is a very powerful flux on silica. And as you'll find out later on, alumina silica mixtures. So potassium oxide is a flux. It decreases the melting temperature. A little potassium oxide goes a long way in forming liquid that encourages sintering. So guess what? In the prior diagram, I said, well, the two-component alumina silica diagram was insufficient to explain what happens in firing. Well, that's because these materials contain some fluxes, alkalis, that increase the melted phase at much lower temperatures than predicted by the two-component diagram by itself. So you can get an idea that these two-component diagrams are helping us understand where some liquid formation takes place. Here's another one thrown in. It's the calcium oxide silica phase diagram. If you make Portland cement, you're pretty familiar with a diagram like this. Wollastonite products, you're pretty familiar with these diagrams. But if you're not, what I want to point out is what happens with silica, which melts up here, close to 1700, 1723. It's denoted on this diagram as the liquidus, or melting point of silica. If we add a little bit of calcium oxide, we reduce the temperature down here to 1436. See, that's where the first liquid forms, where the arrow is, right here. It's denoted as trinamite plus liquid. So we get a little bit of liquid. So calcium oxide is a pretty good flux. So many of the alkaline earth oxides are going to function in the same way, like iron oxide is FeO, magnesium oxide, MgO, magnesia. So we really think about fluxes mostly originating from the alkalis and the alkaline earth elements. So that gives us a practical phase diagram. This is not a real phase diagram, but the dotted lines in the alumina silica system, this is silica, this is alumina, And you've seen this diagram before with the liquidus and the solidus. The dotted lines represent the practical system that's present with alkalis and alkaline earth elements present. So with alkalis and alkaline earth elements, you get a practical eutectic. For all practical purposes, all the elements combined down here around 1170 degrees Celsius. Okay, now you can see that here's a tabulation of what the fluxes do in terms of initial liquid with sodium at 732, potassium down here at 695, calcium oxide at 1140, and iron oxide at 1073. This is about 1070, which is about the point at which alumina, silica, calcium oxide, alkalis, and iron oxide would give you a practical eutectic down here. So you're going to find out that most crude ceramics are fired up in this area around 1050 to 1070 to maybe a little higher degrees Celsius, taking advantage of that eutectic to form the glass to make the product functional. Well, that's pretty easy. So even if you didn't like these phase diagrams, you can look up these melting points in references like Grimshaw and figure out what the effect of fluxes is in your system. Now we're going to go forward into three-component systems. Three-component systems are ones that can generally be used in most ceramic mixtures because two components R3 form the major mineral phases that are present in the system. But if it's two components, we can use the third component as the most active flux and see when melting is going to take place. So nevertheless, this becomes important to us in trying to figure out what's going on. Now, what if you wanted to know what would happen with 7 components? Exactly what would happen? Well, there are computer programs that allow you to do that, including those that are available for the desktop machine, your PC. Some of them have to run on higher powered machines than that, but nevertheless, there are systems that do that, but there are physical property determinations that are alternatives to using these very complex computer programs. And this is particularly thermal dilatometry. It will tell us when shrinkage begins. It will tell us when the multi-component eutectic takes place. But we're going to look at three-component systems anyway, and remind you that we have high flux systems or vitrified systems where the alkalis, alkaline earths, and other fluxes control vitrification, provide for vitrification. And if we put enough heat work, we get enough melting, we cool the product off, we've made a vitrified ceramic. It's going to contain crystalline material of some sort. Now, in systems that don't contain much flux, we can make additions of fluxes in precise amounts. And that's the way that we control the amount of liquid that forms in heating. So we're adding fluxes on purpose into the system to control melting. Wow, that's kind of a new concept. And let me say that that's practiced every day in ceramic arts, ceramic technology. So let's look at a three-component system. This is the system calcium oxide, or lime, as I call it, magnesia, silica. Lime is a very broad term in ceramic technology. It can refer to calcium oxide, burnt lime, caustic lime, somebody might call that. It can refer to calcium hydroxide, which some people might call ag lime, agricultural lime. So you have to be careful. Even in agriculture, people can refer to limestone as lime, calcium carbonate as lime. But I'll always refer to lime as the oxide. So nevertheless, Here in this diagram, the lime axis is here, the lime component is here, the magnesium oxide component is here, and the silica component is here. So we have a 3-component or triangular phase diagram, and we're looking down on the top of the liquidous surface. So if we project an axis out towards you, towards your eyes, that would be the temperature axis coming towards you. And so we have little lines of constant temperature that are plotted on this phase diagram. We also have triangles that are compatibility triangles, and there are many of them on this diagram because this is a fairly complex diagram. We're going to reduce it. And these are compatibility triangles that tells you what is present for a composition at equilibrium if it's within one of these triangles. We have some compounds. Here's one, MgO.2SiO2 in oxide notation. That's the mineral feuchterite. So you can see up here the mineral names that are present. Here's another one, MgO.SiO2. That's the mineral enstatite. Well, I don't want to make this complicated by using these mineral names. We only need to know a couple of them, and we're going to concentrate on feuchterite, magnesia, and a compound that's over here called monocellite, CEO.MgO.SiO2, monocellite. So we're really interested in this part of the phase diagram because we're going to pretend that we're making a composition that's at around 90% magnesium oxide. But now we have 2 fluxes present with respect to centering. These are silica and lime. So we're going to look at this. And even though this diagram has a lot of compatibility triangles and a lot of eutectics and paratectics in it, we're going to simplify it. So we're looking down at the liquidous surface. The next diagram is a perspective drawing from Bergeron and Risbud. And this perspective drawing says that the 3-component system is actually made up of 3 2-component phase diagrams. For example, A to C is the phase diagram between A and C, and the liquidous surface goes like this. The A to C phase diagram provides a eutectic right here. In a like manner, the A to B phase diagram is here, bounded by this side of the phase diagram. It has a binary eutectic here, binary meaning 2-component. But notice also that given a dotted line, there is another eutectic here inside of that volume element, and that's a ternary eutectic, 3-component eutectic. So by mixing the 2 minerals with a third, we get a lower eutectic here in this example than we had with any of the 2-component systems. So that's the reason that we look at 3-component phase diagrams, is it tells us where 3 different substances can interact and give us a lower eutectic. Now, not too important for today's lecture, but really important for you is how to locate a point. So there are 2 ways to do it. If we have a point on the diagram and we want to see what the composition is, we can measure the distance A. That's actually A direction is in this direction right here. That distance we can measure from the point over to the axis in the B direction here. And we can measure from the C component in the direction of the AB axis. This direction right here, this dimension right here is C. So the percent C is the dimension C divided by A dimension plus B dimension plus C dimension times 100 to express it as a percentage. So that's the composition. That's one way to do it. It's not the way that I do it. The easiest way to do it is to say that all compositions that contain C are represented by horizontal lines across here. So if I draw a horizontal line through the composition of interest, then I can look up here, and this is 20, 40, 60% C. 20, 40, 60% C. Then I can draw a line here parallel to the AC axis that represents the percent B, and the percent B looks like it's about 30% B. Okay, so once I've got that point plotted, then I know the percent A, I know the percent B, and the percent C is just the balance going to 100, or I can draw the other line if I want to. So locating a point is easy, but really not required for us today. Now, as I said, we are going to make something where my laser pointer symbol is down here close to the MGO axis. But I want to point out that there are various compatibility triangles. We're going to end up using the compatibility triangle between MGO, forsterite, the compound here, and monocellite, the compound that's right here. Now, I know there's some sub compatibility triangles in here. We're going to explain those in a bit. But basically, what this says is my final fired composition has to be bounded in the compatibility triangle between the major components of MGO, forsterite, and monocellite. Now I'm going to explain this triangle in a little bit more detail as we go along. It's not too difficult. Let's look at the phase diagram. Remember, a three-component phase diagram is composed of three individual binary phase diagram and what happens in between. So here's the MGO silica binary phase diagram. Okay, so it tells us that forsterite melts up here at about 1890, but the MGO melts up here at about 1890. The forsterite melts down here at 1557. So given that, we can see that the side component of the phase diagram is given by this binary. Now, I have stated this wrongly. The forsterite melts up here at 1890. I regret that I made that error, but nevertheless, this is the phase field forsterite plus liquid. This is the phase field periclase plus forsterite, and here's the melting point of forsterite. As we get more silica, you can see the liquidus declines quite a bit down here to the melting point of something called enstatite. This little perictetic point right there. This is the eutectic, and we have another eutectic over here. I'm just trying to make the point that we can look at the phase diagrams between the binary components before we look at what happens within the ternary diagram, the three-component diagram. We can also look at two-component diagrams within the three-component diagram. So this is the diagram connecting monocellite with forsterite. So the line connecting those two is straight across here. We'd call that the join between monocellite and forsterite. And you know that just a minute ago I said our final composition is down here. We're going to look at the MGO forsterite monocellite compatibility triangle, but it's really composed of 1, 2, 3 little compatibility triangles. And the reason these are drawn here is there are different points here where liquid can form. And nevertheless, you can see that liquid forms right about here in temperature space, and that's right about the melting point of monocellite. So nevertheless, we're going to use the larger compatibility triangle in figuring out what's going on. But we can have two component diagrams that we can refer to that go across three component diagrams. And we can use those. So where's the initial melting in this system of high MgO compositions? Well, MgO melts at a very high temperature, much higher than you can ever get in a gas-fired kiln. Forsterite down here around 1890. Monocellite down here at 1485, and some other things that could be present in non-equilibrium conditions. So what if our maximum firing temperature that we can attain is 1550? Then we have to rely on monocellite to be present or fluxes. We're going to assume for a few minutes that these fluxes are not there, and these are usually pretty high purity systems when you are firing these magnesia lime silica systems to make a product. So I know that you can get magnesite or magnesium oxide that's natural, that contains a lot of iron or other impurities, but we're going to assume that we're making this object out of synthetic magnesia that was made from brine, calcine, turned into caustic magnesium oxide, briquetted, fired to very high temperatures to form high purity magnesia aggregate. So in order to understand this, we have to look at a section of the three component diagram. Now you'll remember that the compatibility triangle that we were using before was extending from down here at MgO up to forsterite, over to monocellite, and back down. But I want to point out that this diagram, which I've magnified a lot, and it's a little bit fuzzy, and what you're looking at has other melting points, paratectics and eutectics. And so these are labeled A, B, C, D. And these melting points are down here at 1336 up to about 1490 or thereabouts. So some of these melting points are lower than the melting temperature of monocellite, even though these areas on the phase diagram are not within the compatibility triangle of the final composition. So here's an important principle. On heating a ceramic composition, non-equilibrium liquids outside of the compatibility triangle can form and aid in the centering process. Now, these in this circle are more likely because they're closer to the compatibility triangle, but we can't rule out liquid forming down at a composition represented by A up here. So we could have other minerals formed in the process of firing, even though they're not equilibrium phases that we would expect. Well, that's a very important point. And guess what? That's exactly what happens. So we have a reaction path. And the reaction path is the first liquid forms up here somewhere. It's a non-equilibrium liquid. And the composition of the liquid has to go toward the final composition. The overall composition is right down here where the star is. But the second phase composition, the liquid, starts here. And so if that liquid started at point A of the previous slide, then we would have a phase here. These phase names are over here that melts as low as 1391. Up here with forsterite is 1485. So, that's close to 100 degrees Celsius different, not quite 100 degrees. So melting starts here. The first liquid, wherever it starts up in here, changes in composition as firing progresses. That liquid aids us in sintering by dissolving some of the MgO, which will eventually form forsterite, and maybe a little bit will be present in the solidified liquid in the final composition. So the material is changing, the liquid is changing, and the final composition is over here. We get what we're calling transient liquids. We're going to call them transient, temporary liquids that may not be present because in the final composition, nothing should be liquid below 1485 without other fluxes being present. But we can start melting at 1391. So that leads us to our interesting key point. On heating a ceramic, we can have non-equilibrium phases form, liquid phase or solid phases. And if it's liquid formation, that's going to happen at the lowest eutectic in the system, even though that eutectic might be out of the bounds of the compatibility triangle for the final composition. The final composition is where the system's going at high temperature. It shows us the direction. It shows us the path, but it doesn't show us the starting point. The starting point can be somewhere else. A very important point in sintering. So in summary of heating MgO, lime and silica, even though the system is pretty complex to figure out what's going on, you need to think about what minerals would be in the final composition. So plot your composition. Look what's in the compatibility triangle. In this case, we found out it'd be magnesia, sometimes called periclase, forsterite, M2S, and monocellite, CMS. So that's what we're going to have finally. And we would expect liquids above about 1500, the melting point of monocellite in sintering, but we actually get them at a lower temperature. And there's a reaction path from where the first liquids form. And as MgO dissolves in those liquids, the composition of the liquid changes and the liquid can actually disappear or be, as some people call it, reabsorbed. Sintering begins. So you're outside the compatibility triangle. Well, that's a new way of looking at phase diagrams. That's not equilibrium chemistry that we're looking at. That's not the final fired chemistry. We're looking at a reaction path to get to the final chemistry. Interesting to me. So in summary, for this class, we've used 2 and 3 component phase equilibrium diagrams. We've shown how to locate a point on the phase diagram. We've shown what liquidus and solidus surfaces are, eutectic, lowest melting, peritectics. We've looked at these because we want to find out where the first liquid is formed to aid in sintering. And the most interesting thing to me for you to learn is that non-equilibrium conditions on heating a ceramic for the first time below the melting point allows non-equilibrium liquids to form. These are lower temperatures than we expected. It can be outside of the compatibility triangle. The final phases in the product are probably close to those denoted in the compatibility triangle for the overall composition. But don't forget, even though liquids can be reabsorbed, they can be present in the final fired product as solidified liquids or glass, amorphous phases in the final product, because sometimes the liquid is not completely absorbed. Now look, you don't have to be an expert in phase diagrams, but but you do need to use them. I spent my career teaching this course to link chemistry to mineralogy to phase equilibria. It's really pretty elegant to look at all three of those together, and that's what we're doing in the first part of this course on firing. You don't have to be an expert. You just look at the map and say, here's where the final composition should be. That should be denoted by X-ray diffraction in the fired product. Okay, but you need some liquids in firing to aid in sintering unless you're trying to work with a very high purity system where you don't want any liquid at all. Liquids are going to aid in sintering, and that's the bulk of all the tonnage of ceramics that are manufactured in the world using vitrification, sintering, or reactive sintering. Now, later on, we're going to use those thermal analysis methods, and we're going to start next week, next class that you take. Next time, we're going to talk about firing crude ceramics, clay products, which would include bricks and tiles, roofing tiles, flooring tiles that are made out of solely clay. We're going to go forward and talk about ceramics using very high or higher purity minerals like feldspar and ground sand, or potter's flint it's sometimes called, and clay. Each has a function in the composition. We're going to talk about firing alumina ceramics or porcelains, alumina porcelains, and we're going to get to firing cordierite. So that's where we're going in the course. Please review this class as you might find necessary. If you know a lot about phase diagrams, great. If you need more information, look at the American Ceramic Society's little web accessible description of phase diagrams, or by Bergeron and Risbud, and you will have achieved quite a lot more. So next time we're getting into more practical aspects of firing. We finished the introductory section on materials in firing, and we're going to start talking about specific products to help you understand the strategies that you use in making those products. I'll look forward to our next class.